accelerates objects along a straight line. Force, net force, right? And actually, I probably ought to put a net on here. Okay? Now, what's moment of inertia?
It's mass times velocity squared.
Not quite. To some of your MR squareds. Okay? You need to get used to that.
Yeah.
But you need to pretty much know that for the test that's going to come up. Okay? Okay? So, if you have a bigger I for a given omega, do you get more or less kinetic energy? More, because kinetic energy is 1/2 I omega squared, right? Okay? I mean, we've just said kinetic energy is 1/2 I omega squared, and we use that as our definition of I. Okay? Just like, okay, so if you got a bigger I, is it easier or harder to accelerate something?
Easier. Wait.
If I put more masses on that thing, is it easier or less easy to accelerate? Less easy, right? Okay? And if I put more masses on it, does the moment of inertia increase or decrease?
Increase.
It increases, okay? So, the greater the moment of inertia, the more mass I put on that thing, the harder it is to accelerate. The less acceleration it'll have for a given force, okay? And the further I put the masses from the axis, the more it's going to increase the difficulty of accelerating it, okay? Or reduce the acceleration response to given torque, okay? Well, this is totally analogous to Newton's second law. Okay? Like, how do you get from net force to torque? Basically, you multiply the net force by your distance from the axis, right? Okay? So if I multiply this by A, I get torque, right? I said it wrong. If I multiply this by R, I get the torque, okay? So there's a very simple relationship between this and this, okay? Now it's a little more complicated because I is like your MR squared, right? And alpha is like A divided by R, okay?
What is alpha again?
We know what alpha is. We've been talking about alpha for months. If you don't know what alpha is, you really haven't noted that we have delta, theta, alpha, and omega all measure what? Angular motion.
Oh, angular acceleration.
Yeah. Now, if you've been calling it A when you're doing angular stuff, you haven't been doing what I told you to do. But, you know, there's an epidemic of that. Okay. Yeah. I mean, there always is. You know, nobody listens to the subtle little things that I beat you over the head with. Okay? If you haven't totally grasped how the equations of uniformly accelerated motion and the definitions and everything between linear motion and rotational motion correspond, it's way past time. Get it done. Okay? The reasoning is so similar that you're probably using the reasoning, which is good, but if you're not using the notation, you tend to get out in the ozone sometimes, okay? So you want to understand the notation. So there's the notation. Okay, well, that's a semi-rigorous definition I'll probably be asking you in the homework to fill in some of the blanks. Okay? But from this example, it becomes pretty clear why you multiply the distance by your perpendicular component of force to get your work. And that should be very clear to you. Otherwise, you're just memorizing formulas and hopefully using them right. You don't have a real foundation. Okay? You're the ninja who can smash walls but doesn't understand the history. Okay? And I told you I wouldn't beat that one to death. I think that's the first time I've mentioned it in a week, so maybe I'm not beating it to death. Okay. So all this tells you everything else you need to know about angular dynamics. It's the whole thing. That doesn't mean that you know yet exactly how to apply it, because there are some shortcuts. There are even some formulas, but you can derive them all from these ideas. Okay? And the simpler derivations, of course, I'm going to ask you to do. Not on this upcoming test, but on the next one. Okay?